So yeah, it's true. I used to work properly in computer graphics as a high school student. Then I entered university and I got obsessed with theoretical computer science, almost in my first year. So it's lasted since then. I'm obsessed with impossibility results in computer science and mathematics. In fact, the very birth of the mathematical foundations of computer science were shrouded in impossibility results. So like Gödel's incompleteness theorem or Alan Turing's unsolvability of the halting problem. So when the model of computation was conceived in the 1930s, people were concerned about, well, what can you do with these machines in principle? So these theories on computability are rather well understood nowadays. And maybe the modern concern is more not just what we can do in principle, but what can we do efficiently, so with limited resources like fast. So really the modern analog of these age-old questions is the P versus NP problem that I teach in my undergrad class on Theory of Computation. And what that question asks, I hope people are familiar with this, but roughly speaking, it's asking whether every problem whose solutions are easy to verify, whether you can also find those solutions fast. So I always think of Sudoku as a very good example of this. If I give you a Sudoku grid filled with all the numbers, it's very easy to check that the solution respects all the Sudoku rules. But given a partially completed puzzle, it's actually difficult to find how to fill it in. It's actually, Sudoku is NP complete, so if you find a polynomial sum algorithm for Sudoku, you settle P versus NP. So I am kind of sorry to disappoint you. I don't know how to attack P versus NP. Nobody does. So what we do in our lab is more like we study miniature versions of P versus NP. So that could mean that we study simpler or weaker models of computation than the fully general Turing machine model. So things like restricted classes of Boolean circuits, decision trees, or propositional proof systems that lie SAT solvers. So these are weak models of computation that you can hope to understand really well, so well that you can prove these limitations of them or impossibility results. And as a consequence, you can conclude all sorts of limitations for widely used algorithmic paradigms. So for example, if you look at some model of computation that can do linear programming and you prove limitations for that model of computation, as a corollary you get that linear programming, let's say, cannot solve NP-hard problems fast. And for many widely used algorithmic frameworks, we do have such limitation already. It's just a sample list of things. Now, of course, we never settle P versus NP by just ruling out one algorithmic framework at a time. It's a never-ending list. But nevertheless, if you can understand most widely used algorithmic paradigms, that's already very interesting and useful for algorithmic design. So this is what our interest in the lab at a very high level look like. And so today I wanted to do like a deep dive into just one line of work that we've been doing in the recent years. Just to give you kind of a flavor of the types of things we're doing. And I really wanted to pick a line of work that is easy to explain. So I picked something that involves a new mathematical pattern that we found. And it's the simplest I've come up with in the last 5 years. So I must be able to explain it to you. I want you to actually see what are we hunched over at a whiteboard? What is it that we day to day are trying to figure out? Because the theory can be a bit abstract. Also, I'm going to explain this line of work in like a weird order. I'm just going to throw at you first a solution. No motivation, just here's something interesting. And then afterwards, I'll tell you what is the problem we were trying to solve. And only last, I give you some motivation for it. So trust me. Okay, so I throw at you a solution. This is an interesting mathematical object that we have constructed. It's a strange function. So let me see. This is, I want to start at the deep end. I'm going to tell you about a construction that was motivated by the hex board game. So I don't know if you've seen this game before. It's played by two players. They alternate placing white and black stones on this hexagonal board. And the white player is trying to construct a white path from the left side to the right side, while the black player is trying to obstruct it and construct a vertical path of black stones. So in fact, in this game configuration, the game's already ended. The white player has constructed a white horizontal path, so they've won. An interesting property of this game is that it cannot end in a draw. So no matter how you place white and black pebbles, if you fill the grid, it's not a draw. There must have been either a white path or a black path in the grid. So this is classic. I think it was invented by John Nash. So I'm going to use this game as an inspiration to define a weird sort of Boolean function. First, I'm just going to dispense with the most interesting property of hex, that it can't end in a draw, and introduce draws. I'm also simplifying this a little bit by looking at not hexagonal grids, but square grids. So bear with me. I want to define a Boolean function. It takes as input let's say a Boolean matrix or a white-black coloring of the grid. So it's an n by n Boolean matrix. And I say that that matrix, the first player or the black player wins if there's a vertical path of ones, so black means 1, that's not too long. So the path from top to bottom is at most 2n steps. Okay, so the height of the whole matrix is n. So if I allow 2n steps, I guess I leave some wiggle room for the path, but should pretty quickly go down the matrix. Similarly, I say the 0th player wins if the matrix contains a short path of zeros or white cells across it. So those are the only conditions when one of the players wins. Otherwise, it's a draw. So here's an example of a matrix that ends in a draw. So there is a black path, but it's too long, longer than this threshold of 2n. Okay, it's kind of weird. So I've now defined a strange function. It takes as input this Boolean matrix and outputs either the first player wins, or the 0th player wins, or it's a draw, which I denote by a star. Okay, that's the end of the construction. Now I claim this is a very interesting mathematical object. So here's the interesting property that it has. Okay, so by construction, it's very easy to certify whenever the function outputs a Boolean value, so a 0 or a 1. So easy to certify in the sense that if you only knew where to look, you wouldn't even have to read the whole n squared bits of input. You could just, if you magically knew where to look, you might read only linearly many bits, or 2n bits at most. In this example, all of these bits are 0, so they form this white path. I call it a 0 certificate for the function. If this pattern exists in the input, the function has to evaluate to 0, no matter what is written in the other bits of the matrix. So I hope you see, by construction, I've made it easy to certify whenever the function outputs a 0 or a 1. So in kind of notation, I would call the 1 certificate complexity of the function is at most 2n, and similarly for the 0 certificate complexity. But what's so interesting is I claim that draws are hard to certify. So that's kind of interesting. It's an object where something's easy to do, yet on the other hand, I claim draws are hard to certify. Okay, so it's some sort of a separation, not of P and NP, but of certifying one thing versus certifying another thing. So let me discuss why is it that draws are difficult to certify here. So here's a sample input to this hex function. It's a drawn input, so it's an x that maps to a star. So what it has is a very long black path kind of snaking around, taking order n squared steps inside the matrix. So it's way too long. So it's a drawn input. And I claim, looking at this matrix, it's really hard to certify it's a draw. You have to, there's no shortcut. You have to look at almost all the bits of the matrix to convince yourself this is a drawn configuration. And I'll prove it to you, okay? Inaugural lecture with a proof. So I claim, if you want to certify that this is a drawn input, you have to read almost all of the black cells in this picture. So I claim if you pick any one of these black cells, let's say this one, your certificate has to include that cell. Because if you didn't look at this place in the input, you couldn't distinguish between the current input and one where that bit was flipped, in which case I would get another input that had a short horizontal white path. This white path, if it existed, would be a win for the 0th player. So if you want to convince yourself this input is drawn, you have to look at almost all the bits of the matrix to kind of block all of these short horizontal paths. Okay, that was the proof. You needed looked at a lot of bits to see that this was a drawn input. But I want to go a little bit further. This was too easy. I got this separation of like certifying Boolean values, linearly many bits, certifying draws, n squared bits. It's almost what I want. Secretly, you don't know what I want, but this, I'll tell you, I want a little bit more. So what does it mean to certify something's a draw? You have to really certify two things. You have to certify the 0th player doesn't win and that the first player doesn't win. So I introduced these two notation for the certificate complexity of ruling out one player not winning. And in this input, it was already hard to certify the 0th player didn't win. The proof I gave you really says, just to rule out the 0th player, you had to look at most of the bits. But unfortunately, and I don't like this, it's still easy to certify that the first player doesn't win. For this input, I claim there's a short certificate whereby we can convince the first player doesn't win. So a certificate that shows that there cannot be a short vertical path of blacks. So I actually want to ask, can somebody tell me what is that certificate? Where part of this matrix should I look to very quickly convince myself that there's no short black path down the matrix? And look at only linearly many bits. Let's try that.
Any path has to go through one of those stars, the black bits rolled in a row, and so you only need to look at the thing before it to convince yourself you already did 2n.
Yeah, that's exactly right. So you could just include in your certificate like a couple of the top rows, let's say. If you look at those bits, okay, you already see that any path consistent with these bits have to wiggle around a little bit. Even if you can take a shortcut out of the bits you didn't see, you've already traveled more than 2n steps. Okay, so what I really want for this function to satisfy is actually that both of these certificate complexities here are large simultaneously. So here's the real kicker. The real solution is I look at another drawn input. So now I've put in root n many snakes. Each snake takes up some root n columns. And I claim this is a hard input. Okay, not necessarily n squared as I had before, but now both of these certificate complexities are at least superlinear. Ideally, maybe I would like n squared, but this is the best I can construct and prove. the argument for why these numbers work is not difficult. I don't have time to do it here. It's a one-paragraph argument. But let me just now say, how did we circumvent the problem from the previous slide? What would be now a certificate that the first player doesn't win? Okay, previously we looked at few of the first rows. Now, if you do the calculation, you kind of have to, certificate would have to involve root n rows, so that each of the snakes that you're seeing, travel linearly many steps. And you can formalize this to say that actually any certificate has to be of the same size as one of these guys that are only using union of rows. Okay, so I leave all the technical stuff at that and say, this is our interesting mathematical object. We've constructed a function that separates certifying draws from certifying winning conditions. And there is some polynomial power 1.5 gap there. So actually, if I modify the function a little bit, I do get a quadratic separation, which is optimal for this kind of a question. But this begs the question now, what did we just solve? What am I doing? Why am I being paid to do this? Okay. I can't answer all of those. I'll just tell you what was the problem that this is a solution to. Okay, so we exhibit this strange function with a quadratic gap. And when we started work on this in 2020, I knew that if I could construct one of these weird objects, I think I knew this already in 2016, is that if I only hit this with a technique called lifting, which is what I basically dedicated my PhD thesis on. Maybe you remember from my job talk some 5 years ago what lifting is, or maybe not. Maybe I'll just give a reminder. It's a set of techniques that you can apply to complexity results in weak models of computation. So we proved sort of a separation in a weak model of computation, where I was only allowed to look at individual bits of the input. That's like query complexity. And these lifting tools, they're big, heavy hammers. They allow you to convert such complexity results into complexity results regarding stronger models of computation, like communication complexity. So from this, we get some optimal lower bounds for something called the click versus independent set problem in communication complexity. It's a problem that admits, in fact, many equivalent formulations. There's an equivalent formulation using graph theoretic language, something called the Allen-Saximo problem. So that's the one I want to actually define carefully. So this is the problem we're eventually going to solve. So, okay, so this was a purely graph theoretic puzzle that was proposed in 1991 by these three mathematicians. They conjectured this general relationship for every graph between its chromatic number and its bi-click partition number. So chromatic number is kind of standard. It's asking how many colors do I need to color the nodes of a graph so that there aren't any monochromatic edges. So each edge has differently colored endpoints. What's the least number of colors I need? Bi-click partition number, less studied property of a graph, best explained maybe by a picture. So here I have a complete graph on maybe 6 nodes. And I want to look at what's the best way to partition the graph into bi-clicks, so complete bipartite graphs. And I've done it here. I've colored the edges into different color classes. Each color class is a bi-click. So for example, if you look at the yellow edges here, they form a complete bipartite graph between this node and these nodes. Okay. And the question is, if I want to partition the edges of a graph, how many of these bi-clicks do I need to partition the edge sets? There's an old theorem by Graham and Pollack that says if you have a click of size n, you need n minus 1 bi-clicks to cover. It's quite a lot. So what Graham and Pollack says is that the this conjecture holds for when G is a complete graph. And that's actually how Allen, Sachs, and Seymour said that they wanted to just generalize this Graham-Pollock theorem. Held for a complete graph, maybe it holds for all graphs. Okay, so this conjecture stood for some 20 years until, so it was first disproved by Huon and Sudakov. Sudakov is at ETH right now. So they gave some, like a weak counterexample for it. But now in this line of work, ending up with this hex construction, we're able to construct the optimal counterexamples to this conjecture. So we're able to construct a graph whose chromatic number is, well, a lot higher than its biclic partition number. So this is some quasi-polynomial function of the super polynomial function of the biclic number. It may seem like a weird sort of a function, but it's optimal. It's been known since the 90s that this is the largest gap you can have between the two quantities. Okay, so this was one of the kind of equivalent formulations of the problem we wanted to solve. And I think it's very satisfying to kind of resolve a 30-year-old project and then find an optimal grasp for this problem. So that's already nice, but I want to give more motivation. And it's also why I picked to talk about this, is that when our hex problem was done, I thought, okay, that's it, we move on. But there was actually some interesting subsequent developments I didn't expect that used these Allen-Sachs-Seymour counterexample graphs for other applications in computer science. So I just want to mention a few of these applications as more motivation for this, constructing these weird objects. So the first consequence is in computational learning theory. So I want to highlight some papers that are not even by me, but they're using our constructions. So there are a couple of papers that wanted to develop a general theory of learning, not of total functions, but of partial functions. So traditional pack learning is defined for total functions, but partial functions do arise. Here's maybe the simplest example. Maybe you want to learn some kind of linear classifier with margin, some kind of a linear separator on the plane, let's say, and you're given positive examples and negative examples to your learning algorithm, and you're guaranteed that those samples don't come too close to the line. So there is some kind of margin here where samples are not coming from, so they're well separated. So formally, I would be here looking at a function that maybe evaluates to 0 here, 1 here, and here. In this forbidden band, it's undefined, or there's a star value. So to learn a function like this, I'm guaranteed to only be given these Boolean samples, not anything from the stars. Okay, so they wanted to develop a general theory of learning for such partial functions, and one of their main results is that the theory they developed is novel. It's an interesting new setting that does not reduce to the classical total function learning theory. And to prove this main result, well, they used our weird graphs to prove this separation. And in fact, the proof is very simple. I can sort of sketch a little bit what they do. So they take one of our weird graphs, and they construct a function family out of them, the hypothesis class of functions you're supposed to learn. And in that class, you just have one function for each of the nodes in the graph. Okay? And to define the functions, like I do in this matrix, each column here is obtained from one of the biclics in the graph. So this column, for example, is coming from the yellow biclic over here. So it's something like I put a 1 in here if the corresponding node is on the left side of the biclic. I put zeros for nodes on the right side of the biclic, and I put stars for nodes that are not involved in the biclic. So every biclic gives me one column in this matrix, and that defines a function family. And what they observe, and it's not hard to prove, is that this family has VC dimension 1. So that's VC dimension is the measure of how efficiently you can learn functions in this class. VC dimension 1 means you can learn them with constantly many queries. Yet the class does not reduce to any total function class. So if you try to convert this class into a total class by replacing these stars with Boolean values, no matter how you try to put Boolean values for the stars, you're going to get a family with VC dimension unbounded. So you kind of lose the learnability property. So this is one of their main results. It's a simple application of our weird graphs. And this gap, it readily follows from the defining property of this Allen-Sachs-Seymour counterexample graph, just the gap between the chromatic number and the bicyclic partition number. I want to point out this funny thing is, for the first paper, one of the authors is Gödel. So it's ironic that he got to use those graphs that he conjectured didn't exist. Okay. Okay, so I want to mention one more application of the hex construction. Again, kind of unexpected. I was contacted by a colleague in Oxford who does automata theory. So didn't used to do research on it. I do teach it to undergrads. Maybe I have former students in the room. Can those former students tell me what's the language corresponding to this automaton? I know it's quite late. It's a non-deterministic automaton. What's the language? Yeah.
Give us a string that finishes that has one and then two other characters?
Yeah, so it's like you're looking at the third symbol from the end of the string. If it's a 1, we accept. Okay, so it's a non-deterministic automaton, but actually it has this weird, interesting property. It's unambiguous. So it means that on any execution, the automaton there's only at most one accepting computation. So non-deterministic machines would generally have many accepting computations, but unambiguous machines have at most one. Okay, so now automata have been studied since late 50s, and I didn't think there were any open problems about them. So I was surprised to learn that actually there are some basic questions that are still open about these unambiguous machines. They kind of sit between deterministic and non-deterministic automata. And there was only recently a result that said that complementing unambiguous automata is kind of difficult. So there are some automata that if you want to kind of construct the machine for the complement, you need to blow up the number of states from n states to something that's slightly super polynomial. And this was only, such kind of result was only proved, 5 years ago. And I was flabbergasted that this had not been addressed. Well, now it turns out if we apply this hex construction to this problem in our paper with Stefan Kiefer and my student Wei-Chang Yan, we can improve this a little bit. So from slightly super polynomial to honestly quasi-polynomial. This is the quasi-polynomial is the same quasi-polynomial as in the Allen-Sachs-Seymour problem. For that problem, it was tight. I mean, there was an upper bound. Here, when we've reduced the hex problem here, we don't know if this is tight anymore. The best upper bound here actually is still exponentially large. This is the simplest open problem about automata that I know of, is, okay, which is the right bound? Okay, so that's the story of hex, of how kind of computational complexity theory considerations for, a board game. It can have now all these implications in seemingly different problems in not just in complexity theory, but graph theory and learning theory, which is very surprising to me. Okay, so I thought this was a very, very nice whirlwind tour of different things that happens in our lab. Again, most generally, all I'm interested in, if you have a simple model of computation, I just want to understand it so well that I can put some limitations on it and understand what can't you do with this model of computation. So I try to indoctrinate my students to this way of living. I think many of them are here today. Yeah, so I want to thank all my students also for making my job so much fun. Okay, so thank you.